section 19.1, balancing redox reactions. So in this section, we're going to learn some technical aspects of balancing reduction-oxidation reactions. Let's remind ourselves from Chemistry 1 that certain types of reactions involve the transfer of electrons. And so I'm going to write out an equation for a specific reaction that involves the transfer of electrons. And let's remind ourselves also that we can do what's called assigning oxidation numbers, which is covered in Chapter 4. The section is actually 4.4, where we learn how to assign oxidation numbers. And in that process, we learn that for most compounds, the oxidation number of oxygen is -2. Oops, sorry, this is a chlorine here. And that the oxidation number for potassium is +1 as an alkali metal. So alkali metals have oxidation numbers of +1 in compounds and polyatomic ions. Oxygen generally is -2. And so we can figure out what the oxidation number of chlorine is from the other two elements with the idea that they have to add up to 0. So if the potassium is +1 and the oxygen is -2, but there are 3 oxygens, in order to add up to 0, the chlorine has to be at +5, right? And you can do the same thing on the product side. Generally, in compounds and polyatomic ions, alkali metals are +1. So if the potassium is +1, the chlorine has to be -1. Now, oxygen on the product side is an element, and elements are neutral. They have no charges, so their oxidation numbers are 0. So in this reaction, potassium hasn't undergone any changes. It started at +1 and it ended up at +1. There's no change. However, the chlorine has changed. The chlorine has gone from +5 to -1, indicating that it's gained a total of 6 electrons. Each chlorine has gained 6 electrons, going from +5 to -1. That requires gaining 6 electrons. Each oxygen, on the other hand, has gone from -2 to 0, so that means each oxygen has lost 2 electrons. Right? So that's the idea of a redox reaction, that one element loses electrons, in this case the oxygen, got oxidized. Loss of electrons is oxidation, whereas the chlorine gained electrons, that's called reduction. Gaining of electrons is reduction. Remember, oil rig, oxidation is lost, reduction is gain. Or Leo, the lion goes grr. Loss of electrons is oxidation. Gain of electrons is reduction. Leo, grr. Okay? So that's one particular example. It turns out combustion reactions can also be analyzed in the same way. So if we take methane and oxygen to form carbon dioxide and water, and we analyze each element, well, it turns out our rules of oxidation numbers suggest that hydrogen, with a couple of exceptions, but they're not shown here, is +1 and has an oxidation number of +1. So if there are 4 hydrogens and each one's +1, that means the carbon has to be -4. Oxygen, again, is an element, so it's 0. Over here, the oxygen is in a compound, so it's -2, but there are 2 oxygens, so the carbon's got to be +4. And then over here, again, the general rules are hydrogens +1, oxygens -2. There are, of course, exceptions to that, but they're not going to be shown in examples like this. Those would be more advanced problems. So again, we take a look and we see that in fact the hydrogen, no change, right? Hydrogen started as +1, it ended up at +1, no change. But the carbon went from -4 to +4. Lost 8 electrons. Wow, that's oxidation. Whereas the oxygen, not much room here, oxygen went from 0 to -2. That's a gain of electrons. And so that's reduction. Okay, so that's a review of oxidation numbers as a way to analyze redox reactions. However, the ones we're going to look at in this lecture and in this chapter are not those types of reactions, not decomposition reactions. Oops, sorry, mistake here. Not decomposition reactions. We're not going to look at those, and we're not going to look at combustion reactions. We're going to look at aqueous reactions involving metal ions. So these reactions are occurring in water, and they involve metals and metal ions. This is a redox reaction. Now, what's nice about these types of reactions is that figuring out the oxidation numbers, see how big I'm making these little circles here. Finding out the oxidation numbers is easy, because if it's a pure element, it has no charge, its oxidation number is 0. So these are both 0. But if it's a monatomic ion, the charge of the ion is the oxidation number. So this is +2, and this is +2. So what has happened? The tin has gone from 0 to +2, lost electrons. That's oxidation. Whereas the copper's gone from +2 to 0, that's a gain of electrons. So that's reduction. Okay, very nice. So those are the types of reactions we're going to look at. But let's remind ourselves that we can also analyze reactions using what are called half reactions. This is a different form of analysis, but it can give us very similar information. What's the oxidizing agent? What's the reducing agent? Remind yourself, by the way, that if something gets oxidized, it's the reducing agent. So since copper got oxidized, since tin got oxidized, this is the reducing agent. The one that gets oxidized is the reducing agent. The one that gets reduced is the oxidizing agent. Okay, it's the opposite of what happens to it is the opposite of what it does. Okay, now let's take a look at this other method, which is called half reactions. I'm going to show you really briefly with this one. The way you would do it is you would take the first element, which is tin. I'll leave the states of matter out, and you just write what you see in the equation just for that element. And then you add electrons to the more positive side so that the charges are the same on both sides. So for the tin, it starts off with an oxidation number of 0. It ends with a charge of +2. So it had to lose 2 electrons. So we put 2 electrons on the product side. For the copper starts as +2, ends up as copper. So that means we had to gain 2 electrons. So we write electrons on the reactant side. Okay, that's the half reaction method. Again, that's covered in Chapter 4. So if you need to review that, go back to Chapter 4 and take a look at some of the problems there. You can find them actually, those videos. I have videos for those types of reactions, okay, on YouTube. Now, what I'm going to show you is a more complicated equation to balance. This one's going to be complicated, and since it's so many steps, I'm going to go ahead and take everything, take the states of matter off just to make it simpler to look at and to write out. Now, when you look at this, you may notice something that's odd about it. And by the way, this is a redox reaction, the third type that we just covered. In this redox reaction, there's oxygen on the reactant side, but not on the product side. What's going on? So that's what this is all about. This is called balancing a chemical reaction. It's a redox reaction. in acidic solution. And this is a very standard type of problem, how we balance a redox reaction in acidic solution. Okay? We can also do it in basic solution, and when we do it in basic solution, there's an additional step. So what I'm going to do is I'm going to number the steps just like your textbook does. And the first step is to separate them into half reactions. And again, the way you separate them into half reactions is you take one element at a time. So iron is one of the elements, and you just copy down what you see in the equation. Okay? Now, I'm going to do the other one as well. The other one is chromium. And I'm just going to copy down what I see in the equation, reactants and products. Now I'm going to now that they're separated, now I'm going to balance each one separately. So this is step 2. So I'm going to do the iron first because it's easy. And here's how you balance. You first balance with, by checking to see there's the same number of atoms on both sides. So for iron, again, I'm going to do this one first. How many atoms are on each side? There's 1, right? There's 1 iron on both sides, so that's balanced. The number of atoms is balanced. Next, I'm going to balance charge. And the way I'm going to balance charge is by adding negatively charged electrons, right? Electrons are negatively charged. And I'm going to put them on the side that's more positive to balance the charge. So if you take +3 and -1, that's +2, which is the same as we have on the reactant side. So now we've balanced charge. Now I'm going to do the second half reaction. I'm going to balance the dichromate ion. This is called dichromate. This is going to be more complicated because it has oxygen. And here's how you go about dealing with the oxygen. You count the number of oxygens on both sides of the equation, and you add water, H2O, to the side that has fewer oxygens. Now, why would you do that? Why would you add oxygen to the side that has fewer oxygens? You do it to balance the oxygen, but we do it in the form of water. I'm going to add 7 waters, because 7 oxygens is what we have. Now I'm going to balance the chromium. How many chromiums are on the left side? How many chromiums are on the right side? There's 2 on the left, 1 on the right. So we put a 2 here, right? Does that make sense? Now there's 2 chromiums on both sides and 7 oxygens. Of course, you'll notice that by adding 7 waters to the product side, we've now added hydrogen to the product side. And there's no hydrogen on the reactant side. So what we do is we add hydrogens. How many are there? 14, not 7, 14. There's 7 H2O, that's 14 hydrogens. But this is an acidic environment, acidic solution. Acids mean H+. So it's 14H+ we're going to add. And that's the key. In these reactions, to make them go, we have to add an acid like HCl. Okay? Now we've got 14 hydrogens on both sides. So now we've balanced chromium, oxygen, hydrogen. The only thing left is the charge, and we use the same logic we used before. You add electrons to the more positive side. Now I need more room over here, and I'm going to add the electrons over on the reactant side. So I'll leave a little room over here. This one's not so simple, right? Because you've got 14 positive charges, but you got 2 negatives. So if you add those together, you get +12. And then on the product side, you got 2 chromium 3s. So that's +6. And then you got 7 waters. I'm not worrying about that because those are neutral. They don't have any charge. So how many more electrons do we need to add to the reactant side? It's 6, right? Why is it 6? 6 negatives and 12 positives is +6. And that's the same thing we have on the product side. So we've now balanced the electrons. So what do we do next? Next, step 3, is we count the number of electrons in each of the half-balanced equations, the half reactions. And we equalize them by multiplying through the equations so the electrons are equal in each half reaction. So we have 1 electron in the first half reaction, but 6 in the second. So what I'm going to do is I'm going to take the first half reaction and I'm going to multiply it by 6. What happens if I multiply that by 6? I get 6 iron 2s goes to 6 iron 3s and 6 electrons. Now the electrons are equal. Now I recombine. Half reactions. Cancel anything that's on both sides. Sometimes when you do that, you'll have to cancel waters. Sometimes you'll have to cancel H pluses. In this one, we only need to cancel electrons. So here's what I'm going to do. I'm going to take each of these half reactions. There's one. And I'm going to take the other one, which is all the way up here. And I'm going to combine them. Okay? So everything that's a reactant gets added together. Everything that's a product gets added together. So on the reactant side, oops, sorry, I forgot that the one that we're going to add is actually this one down here. Sorry, because we had to multiply it by 6. So combining them, you have 6 iron 2s. Over here, we got 6 electrons, but our 6 electrons are going to cancel, so get rid of those. 14 hydrogen ions and dichromate. Is there anything else on the reactant side? That's pretty much everything, right? H plus, dichromate, and iron. Now we do the product side. On the product side, we have 2 chromiums, so 2 Cr3 plus, 7 waters, 7 H2O, and then we've got 6 Fe plus 3. Again, the electrons cancel. We have 6 electrons on both sides. So this is our balanced balanced redox reaction. Okay? Pretty involved, right? But it's not that hard if you practice it. So here's essentially what you're going to do. 1, split half reactions. That's easy enough. 2, balance each separately. 3, when you're balancing each one, you do each element, then electrons. Now remember, you're going to add the electrons to the more positive side, equalize the electrons in the half reactions, and then 5, recombine. And you're done. Oh, I should point out, recombine and cancel. And you may cancel electrons, you might have to cancel water molecules, you may have to cancel H plus ions, but then you're done, and that's it. Okay? Now that's how you do it in a half reaction method in an acidic solution. I'm going to make one quick point. The sample problem goes into basic solution, but if it says in basic solution, you have one more step. After you do everything that you've done so far, 1 through 5, you add OH minus to both sides. And cancel the H pluses. So here's what you do. Let's say we have, I'm going to come back to the previous example. This one's an acidic solution. But suppose you've got 14 H plus. What you would do is you'd add 14 OH minus to it. And that gives you 14 waters. So you would do that to the reactant side. But remember, if you add something to the reactant side, you got to add it to the product side. So this would be on the reactant side. But on the product side, okay, you're going to have, let's come back over here. On the product side, we just have water to begin with, right? So we're going to have 7 waters plus 14 OH minus, right? So look what happens to the water. We now have 7 waters on the product side and 14 on the reactant side. So 7 of those are going to cancel. And they're going to cancel with that. So overall, you would have 7 waters on the reactant side and 14 OH minus on the product side. It's kind of cool. All right, so that's if it's in basic solution. That's if it says that it's being balanced in basic solution. If it's being balanced in acidic solution, you don't have to go through that final step. In acidic solution, you're going to have H plus on the reactant side. In basic solution, you'll have OH minus on the product side. And there you go.